عدة كالنانو تكنولوجي والطاقة المتجددة والنانو فوتونات. والرنين المغناطيسي والفيزياء النووية التطبيقية والكيمياء الحركية، وكذا كلية للحاسبات والمعلومات متطورة، بالإضافة إلى التوجه نحو الإنتاج والتصنيع الذواتي. 20 بعد 100 عالميا، ولتصنف جامعة عالمية خضراء صديقة للبيئة.
واهتماما بممرات مجهزة للمكفوفين تنتهي بمنحدرات ممهدة.
تستهدف المناهج والأساليب التعليمية تعزيزا نوعية وهامة للتغلب على التحديات الفكرية، وكذا تشجيع التفكير الإبداعي وتعزيز. تسعى للشراكة الدولية من خلال اتفاقيات مع جامعات العالم في أوروبا والصين واليابان وروسيا في مجالات علمية مختلفة.
It's a great university with research and many faculties. Because we would like to take a contract and we would like to take a cooperation between the University of Hungary, University of Debrecen in Hungary, and the Kfralshík University. And I think this university growing very, very fast. Last time when I was here, it's not see, it's more with the building and so on and so on. So I think we have a good chance to take a cooperation between the two universities.
As I get another invitation from the president, where even if it is next week, I will come again. I enjoy this visit and I will come again and again until such a time that a lot of Nigerians are here. Or until such a time, you know, there is a branch of this university in Nigeria.
كفرالشيخ ترحب بجميع الوافدين، وعقولنا وقلوبنا ومعاملنا ومدرجاتنا مفتوحة لأشقائنا الوافدين من أفريقيا ومن الدول العربية ومن كل الدول العالمية. في الحقيقة زي ما شفنا النهاردة الإمكانيات التعليمية والبحثية في جامعة كفرالشيخ هي بمستوى عالمي بمستوى قياسي. جميع الكليات مجهزة بمقاييس عالمية طبقا لمعايير القرن ال21، وده فخر لجامعة كفرالشيخ وفخر مصر يكون فيها جامعة بمستوى جامعة كفرالشيخ.
الله الرحمن الرحيم ألم نشرح لك صدرك ووضعنا عنك وزرك الذي
Professor Ali Hbeish, Chairman and former President of the Academy of Scientific Research and Technology, and all of our dear guests. We are delighted to have you here to attend and participate in the 5th World Textile Conference, Smartx 2015. The Textile and Apparel Branch of Home Economics Department, Faculty of Specific Education, Kfralshيخ University, Kfralshيخ University and Ivanovo Polytechnical University, Russia, have all organized this conference, which starts from today, November 23rd, till November 25th, to be held in Kfralshيخ University, Egypt. And that's according to Memorandum Agreement cooperation between the two universities. So thank you for coming. The fact that many of you have traveled long distances serves to remind us all of how important this conference is. We hope you will enjoy our program to the fullest.
The Smartx 2015 Textile Conference has been designed to introduce and discuss technological achievements and innovation brought about through teaching, research, and development activities. Special emphasis is placed on the impacts of these attributes on technical and functional textiles of added value. The conference will provide plenary lectures, oral, and poster presentations. Some of the topics features at the conference will include advancements in textiles processing, biopolymers and biotechnology, textiles for medical application, comfort and well-being, textile design, fashion and style, modeling and simulation, sustainability, finishing processes, color science and dyeing, non-woven, composite fabrics. The event will feature a workshop that will provide an extensive review and technical critical evaluation of the recent advances in weaving and weaving preparation technologies will be provided. The workshop will also cover evaluation of gray yarn and the yarn quality required for high-speed weaving.
And since it's important for you to be aware of the goals of the conference, here are some of them. First dimension, the position of Kfralshيخ University internationally and locally. Number 1, shedding the light on our new university towards internationality. Number 2, putting the scientific status of the Egyptian textile and apparel of the higher levels through organizing the conference. Number 3, the international conference, Smartx 2015, organized by Kfralshيخ University and the Russian University, takes place at the same time, during which Egypt is witnessing a remarkable development in education, and this made education with all its fields take part in the overheated international race of scientific, professional, and academic competition. Second, the scientific research of the university. The conference is an addition to the scientific research as it contributes to increasing the exchange of experience all over the world. Third, university, community service, and environment development. Its main goal is to support and stimulate the scientific community and transferring experiences from one place to another and contributing to develop the scientific and academic community. Fourth, Egyptian tourism. It contributes to promote the Egyptian tourism, the thing that helps increase and raise the economic financing. It also aims to market the Egyptian tourism services to the participating countries all over the world. And before I hand over to Professor Said al-Nashar, our coordinator for Smartx 2015 conference, who will outline the day's events, I want to say once more on behalf of our Kafralshikh University, welcome. It's a pleasure to have you all here. Thank you so much.
I love all of you. Smartx, 5 Smartx to 2015 Egypt World Textile Conference, Engineering, Applied Art, Scientific Science, November 23 to 25, Kafralshikh University. Under respect of Professor Dr. Ashraf El-Sheikhi, the Minister of Higher Education and Science Research, Egypt, Professor Maged Abdel Tawab El-Qimari, Rector of Kafralshikh University, Egypt, Professor Dr. Robert Mitchovich Aloyan, Rector of Ivanova Polytechnic University, Egypt. According our memorandum agreement to cooperation between Ivanova Polytechnic University, Egypt, Polytechnic Russia, and Kafralshikh University, Egypt. Dear guests, Your Excellency, dear colleges, we had established our idea Smartx conference since 2003 with my friend Professor Anatoly Esgarodin, Ivanova Polytechnic University, Russia, while meeting him in Poland. Then we start to the first conference in 2011 in this place in Kafralshikh University, Egypt, according to our memorandum agreement to cooperation between Kafralshikh and Ivanova Textile Academy, Russia, which later had become Ivanova Polytechnic University, Russia. After that, we had established Smartx research journal, Kafralshikh University, Egypt, for many objective general development for blend and use this interconnection between a nation which overall from blendry symphony of transfer of culture. People have always felt communication has acquired a new dimension today due to the development of technology, difficult to predict. The global village of consequency blendry technology development, a consequence of development of society itself. In fact, communication is the secret development of a human society. Developing link between people led ultimately to the general development of society. No community, no culture can be developed without having a link with the other human. One must say that the conference between specialized is the first of all an opportunity to achieve the exchange of knowledge in particular scientific field, respectively textile. But this effect of this meeting have a much greater scientific through the event. It makes an exchange of culture. This exchange of culture is still occurred due to the technology development, but nothing is more important than direct contact. This experience has the total effect of each us. This professional and culture exchange create diversity that the world we live. We are thanking you for coming in our country and the cordially of civilization, and we hope you will enjoy your time in the conference. Many thanks for Professor Ashraf El-Sheikhi, Minister of Higher Education and Scientific Research, Egypt. Many thanks for Professor Maged El-Qimari, Rector of Kafralshikh University, Egypt. Many thanks for Professor Robert Mitchovich Aloyan, Rector of Ivanova Polytechnic University, Russia. Many thanks for Professor El-Sayed Higazi, Vice Rector of Kafralshikh University, Egypt, for giving us the opportunity to hold this conference, Smartx Egypt. Many thanks for our international conference scientific committee members and all organized committee members and all students of Kafralshikh University who appreciate this conference and showed a great cooperation. Many thanks for our sponsor, Kafralshikh University, the first sponsor for us. Professor Muhammad Farid Khamis, Oriental Weaver, Egypt. Professor Mustafa Kamal, the Higher Institute of Applied Arts, Taktour, Egypt. Mr. Muhammad Hassan Abbas, the owner of Higher Institute of Technology, Mahal al-Kubra, Egypt. Our participating countries, Egypt, the organizer of this event. After that, participating countries, Algeria, Australia, Belarus, Belgium, Bulgaria, Croatia, Czech Republic, Egypt, Georgia, Germany, Ghana, Greece, India, Iraq, Japan, Kazakhstan, Morocco, Poland, Portugal, Romania, Russia, Serbia, Slovenia, Tunisia, Turkey, United Kingdom, United States of America. And thank you.
And now, with Professor Said Higazi, Vice Chairman, Vice President of Kafralshikh University.
Bismillahirrahmanirrahim. Dear colleagues in the stage, Professor Dr. Maged Al-Kamali, President of Kafralshikh University, Professor Dr. Ali Hbeish, previously President of Academy of Science Center, Egypt, Professor Dr. Muhammad Kamal, dear colleagues, deans, vice deans, and staff of Kafralshikh University, it is a pleasure to welcome all the conference attendants of national and international scientists on the land of Kafralshikh Governorate and in Kafralshikh University, that university, which is modern university with advanced steady steps toward the scientific progress for both the undergraduate and postgraduate studies, as well as scientific research activities. Kafralshikh University possesses distinguished staff in different specifications and strong educational and research infrastructure, from accredited specific labs, distinct central labs, teaching or great teaching halls and seminar halls, and so on. It is privileged to organize the international conference Smartx 15, not only to contribute recent research papers about textile advance and exchange scientific ideas in this field, but also to display the abilities and possibilities of Kafralshikh University in academia, research, health environment for employees, students, and staff in different specifications, which include agriculture, education with its branches, specific education, physical education, and general education, animal and human health faculties, humanities, commerce, engineering, science, aquaculture, and computer and informatics science. Unfortunately, this conference timing encountered bad luck because of Russian airplane accident and terrorism in other areas of the world that prevent not less than 20 international scientists to come and attend your conference. Also, by this time is run into the Egyptian parliament elections that made some difficulties with residence preparation. Finally, I wish to all success to your conference with applicable scientific benefits and recommendation, and establishing new relations with your colleagues in the world. Thank you all.
And now with Dr. Maged Al-Qamari, the president of Kafralshikh University, Egypt.
Bismillah ar-Rahman ar-Rahim. Ladies and gentlemen, good morning everyone. You are welcome to the International Textile Conference in Kafralshikh University. It is a big event for us. I would like to thank all the guests of honor, partners, speakers, and participants from academia, business, and industry will result in a fruitful exchange of ideas, deepen their global relationships by establishing dialogues for cooperation in science and technology. We have in Kafralshikh University state-in-the-art education, excellence research base, and we have centers of excellence. Yet, we need to think about the possible cooperation together to create a bright future and to strengthen the condition for excellent science, innovation, and higher education in our countries. Today, we should also think about big cooperation in producing, developing, and maintaining leading products. I hope you enjoyed your stay in Kafralshikh, and I wish to all a successful conference. Thank you for your attention.
And now with Professor Ali Hbeish, Chairman and former President of the Academy of Scientific Research and Technology, and all.
Bismillah ar-Rahman ar-Rahim. His Excellency Professor Dr. Maged Al-Qamari, President of Kafralshikh University and Chairman of the conference, distinguished guests, ladies and gentlemen, it is my privilege to be with you in this conference, and I take this opportunity to express my sincere thanks, appreciation, and gratitude to the President of the conference, Dr. Maged Al-Qamari, and his colleagues, notably Professor Dr. Said Higazi and Dr. Said Al-Nashar, for their kind invitation. I thank you all for coming to witness this great event, and I am sure that your contribution to the conference will make it more sounding and useful. Ladies and gentlemen, science and technology are today the engine that can trigger rapid economic growth development and sustain it in the long run. Progress and prosperity can be achieved in the shortest possible time only by vigorous efforts to apply science and technology. The advanced countries are nowadays experiencing unprecedented economic growth. The gap is becoming wider between advanced and developing countries. Both the growth and the gap is becoming wider. Both the growth and the gap are due to production, mastering, and utilization of science and technology. Advanced countries have been adopting scientific and technological achievements almost as quickly as they have become available. Advanced countries have long evolved broad and intensive science and technology infrastructure and have concentrated to graduate education and postdoctoral training and visiting scholar interchanges that have yielded the best in human resource capability. This focus on people and infrastructure have made it possible to record the broad and in-depth science and technology achievements through establishment of national innovation system, which is integrated with national development. In developing countries, however, there have been a number of gaps and deficiencies which had to be overcome, followed by a specific group of actions before such integration start to work smoothly. Ladies and gentlemen, research and development, abbreviated as R&D, represents the most important domain in science and technology system. In the mid-19th century, this term R&D didn't exist. By around 1910, notably in Germany and USA, specialized facilities dedicated to R&D had emerged within large firms, within companies, within the industry. 30 years later, these specialized organizational entities were strongly recognized as important contributors to the technical development in much a wider range of industries. This process of institutional evolution took place within firms, with relatively coherent links being maintained between the emerging R&D activities and all the other engineering, production, and the marketing activities of the firms. Thus, it is obvious that a vast majority of industrial research and development was undertaken within firms in most of the industrialized countries. Different situation is encountered with developing countries. From the year 1950, the countries of Latin America, Asia, and later Africa began to build their own industrial research and development capabilities in centralized institutions that were formed, financed, and operated by the government. The integration of science and technology into sectoral or national development plans within the developing countries therefore requires recognition of where we have been, where we are going, and how we intend to go there. Strategies must be developed and then followed by implementation. Integration doesn't merely happen by itself. To achieve this integration within our time frame is a very complex task indeed, and it requires hard and constant work. Ladies and gentlemen, I hope all the success to your conference, and thank you very much.
And now, with Dr. Maged Al-Qamari, the president of Kafralshikh University, to distribute some souvenirs. Professor Ali Hbeish. Professor Mustafa Kamal. Professor Muhammad Farid Khamis. Professor Abdel Fattah Siyam. Professor Bugoy Kamara Bhara. Professor Sahar Saad.
محمد سعد.
Professor Muhammad Saad.
وشال سين.
Professor Kushal Seen. The organizer of the conference. أستاذ دكتور سيد النشار. And now with a lecture about applications of technical textiles part 1 with Professor Muhammad Saad.
New plants 50, but in this project the emissions will come down less than 20 milligrams. See how? In cement industry or similar industries like all refractory industries, we use two types of filters: electrostatic precipitators and fabric precipitators and fabric filters. Cairo Halwan Air receives around 200,000 tons per year. Imagine 200,000 tons per year in Halwan area only. This is based on 1 million ton per the production line. So what's the problem? Old companies like Halwan, Tora, and the national company in Arabic called Qawmiya, the three companies, all production lines are old production lines. So they use massively the electrostatic precipitator. There's a problem with the static precipitator. First, the idea of the static precipitator is to rectify this rectifying electrode that issues or emits electrons together here with the molecules of the gas deposited on the dust particles, so thus we get positive particles, and thus they are transmitted to the collecting electrode. Here's one sensitive point, that's the resistivity of the dust that plays the role as to make the process safely and smoothly. Let's see this. Electrification produces what's so-called corona discharge. Corona discharge produces electrons with the gas ions, and then with the electrodes, the dust particles are transmitted from the left side to the right side, which is the collecting electrode. That's the red one. Okay? And here we come to a sensitive situation. That's the resistivity of the dust. The desirable situation is to have what's called moderate resistivity. Not high, not low. Because high makes dust stuck to the electrode, and it's very difficult to discharge the dust particles. With low sensitivity, electrons come back, goes back to the rectifying, and we have undesirable situation, that's very high emissions. So the moderate sensitivity is the desirable one that makes discharge of the dust easily when it comes to the collecting electrodes. So let's just see how electrons go back, and undesirable emissions of electrostatic precipitators happen just like this, which goes up to more than 1,500 milligrams. You can compare with the load. We are talking 50 milligrams. It goes up to 1,500. So it was the decision in Egypt to convert the electrostatic precipitator into fabric filter. That's a long story. Please bear with me. Have we done any mitigations to reduce dust emission from the existing cement plants? Yes, we did. First, we increased the surface of the collecting area of the existing electrostatic precipitator, but the emission was still above 50 milligram per meter cubed. Second step, we constructed a new electrostatic precipitator in series with the existing electrostatic precipitator, but the result was not satisfactory. We converted the electrostatic precipitator into a hybrid filter. But, of course, the result was good, something like 20 milligram per meter cube, but still we had troublesome with the difficulty with the maintenance. This is one of the steps, which is 2 ESPN series. That's one. That was built in Katamiya in Suez. What are the main factors affecting the efficiency of electrostatic precipitator? First, resistivity of the dust. Electrostatic precipitator is very sensitive to the resistivity, while fabric filter is not. So, the temperature is one factor that affects the electrostatic precipitator. In electrostatic precipitator, we have to use very high spray water to reach the temperature to suit the operation of electrostatic precipitator. For fabric filter, we can use less amount of water together, water and air, for spraying to let the gas temperature come down from 600 Celsius to 150. That suits the normal polyester filter fabrics, for example. This is the design of the spray we made to suit the fabric filter. Sensitivity to chemicals. Electrostatic precipitator is very sensitive to chlorides and sulfate content. ESP is very sensitive to grinding. You know, grinding is one stage in cement production. So when we do grinding, electrostatic precipitator, there is a problem with this stage. Difficulty to collect particles. Fine particles are not suitable for electrostatic precipitator. Fabric filter can collect so fine particles. You will see that. Risk of explosion. With burning in the furnace, there are some gases like CO, CO2, SO2, and NO2 are produced with burning. So when CO is increased to a certain limit with the existence of corona inside the filter, there is the risk of explosion. You can see one accident here happened in one, and some people, okay, it's working. Yeah, this explosion happened, and a number of people, something like 20, were killed in this accident. Maintenance, filter fabric is much easier than electrostatic precipitator. So it was the decision to convert ESP into filter fabric. The methodology had to be very cost effective. What do you mean by cost effective? Cost effective, that high functionality and low cost. Okay? So we decided to use the same ESP casing, to use the same ESP dust hoppers, same transportation system, same duct system, replacing only the fan of the old system with a new fan to suit the fabric, because we cannot use the same fan of electrostatic precipitator. Why filter fabric? It is a combination of cost-effective design and low operating cost, high availability and high efficiency of dust removal. The theory, simple theory of surface filtration is to collect the dust this way and then jet pulse this way to get a smooth landing. Now we have two kinds of filters or filtration system. Depth filtration, that's to the left, and surface filtration to the right using membrane. You can see the difference here. With the left side, you can see some particles, fine particles are passing by here. For surface, all dust is retained. Now the theory of dust collector as a fabric. I made this and this for people that cannot hear well, so you can read here, okay? And to the right, you can listen well, okay? In both cases, dust-leaving gas is fed to the dust collector upward, downwards, or downwards, upwards. In both cases, the dust is accumulated on the outermost surface of the textile tubes, okay? Only clean gas passes to the clean area, and then after, of course, this diminishes the porosity of the fabric. We cannot do it like this. Delta T control, when it comes to 150 millimeter water gauge, clean air's pulses start to go down and clean the outermost surface and get the particles downwards in the hopper. This is automatic operation. Filtration, pulsing, filtration, cleaning. This operation lasts for 1 year without any stop until the maintenance date comes. So it's very safe with the filter fabric to clean the air. So it was not possible to come to the industrial application without lab scale. So this is one instrument I designed. All parameters in the dust collector you have seen is included here. So filter fabric was characterized by this instrument. Another stage is the design and construction of a pilot scale dust collector. We can use polypropylene, polyester, fiberglass, or PTFE coated textile material. This table shows the design of the new converted filter, depending on such parameters like gas flow, how much? Imagine 630,000 millimeter cubed per hour is clean per hour. 630,000. This is the capacity of the filter. Total bags per row, 168. Total bags, 2,352. Bag diameter, 149 millimeter. Bag length, 8. Then, from such the calculation of this, we get the total filtration area, 2,805 meter square of textile material, designed as tubes. Dividing this by this number, we get what's called air-to-cloth ratio. The air-to-cloth ratio is the main parameter of designing a filter fabric. Okay? So the engineer should know air-to-cloth ratio, how much, depending on the area, depending on the capacity. The steps of converting the electrostatic precipitator into fabric, first is to cut off the roof and then strip off all steel parts inside the filter. Design the cleaning system. Install new bags, new bag plenum and new bags. 4 adjust filter bags. Number 5 is to replace the fan. That was the last step after converting. This video shows when the filter was transported on its tower to start working. This is the last station of the filter. You can see it as a house, small house. In power generation, we use pleated filter bags for larger filtration area. With filter fabric, we come across with some technical problems during the installation, like rupture of the membrane. So when we install the filter bags, we have to be very careful because this is a very expensive material. The most expensive part in the filter fabric is the fabric itself because it's replaceable. And when we talk about a membrane coated textile, this is a very high cost. Now you can see the converted filter and the comparison between ESP chimneys and the fabric chimney. This is Intora Cement Company with 20 milligram per meter cubed emission. This is a chimney or a stack in December 2013 in Helwan Company. The same stack after conversion in March 2015. This is the map of pollution in Cairo. Now, we are finished with the project, still only 1 or 2 production lines in the area to have it cleaned, and dust emission is less than 20 milligram per cubic meter. If there's anybody to thank, we should thank Egyptian cement companies and the multinational companies for their interest in this project. WEEE for supporting us, World Bank and European Investing Bank, and thanks for textile, and at last, thank you very much.
Their potential applications with Professor Abdel Fattah Sion.
I have here a team of researchers, one Julia Ramos from and Amanda from University of São Paulo School of Arts, and Mohammed Yudani is one of my students at North Carolina State University. This work here is funded by a program called Global Partnership Network. This program involved collaboration between 3 universities, and we hope that more would join. Every university fund the professor from the university and students, and we collaborate with other universities who funds also their student and professor. We were able to get a fund from this program, and I have Amanda, student from São Paulo University, working on this research here, and she done most of the work. I also would like to thank the company Ashland for providing the resin. Green composite is going to be a must sooner or later because synthetic fibers made from petroleum is definitely depleting. Whether we have, sooner or later we are not going to have petroleum and then petroleum-based fibers, we have to find an alternative for them. These are the high-performance fiber, and we use large performance to do such products like boats, windmill. These are applications today. Application also expanded recently to building structures. Application of composite expanded many years ago to military application, truck application, biking, and the reason for that, as you all know, composites are lightweight and they are substitute for heavy metal, and as such, we can get more mileage for our cars, our planes, our rockets. that go to outer space or shuttles. What's the driving force for this? As I mentioned, the current commercial composites are made from petroleum-based synthetic, and this have negative impact on the environment. And the high price of petroleum nowadays is not really a high price, but it's going to go up sooner or later. The drastic reduction in world reserve of petroleum is another reason, and the cost of disposing petroleum-based composite is skyrocketing. Natural materials are renewable. They are friendly to the environment, inexpensive. We throw them away for waste, and they are environmentally friendly as such. If you look at previous research on composite from natural fibers, it's still limited, and we still have issues because natural fibers are not uniform. We limit this to non-woven. Parallel yarns, we will just put the yarn manually, and layer to the woven fabric is also one of the methods that converted. Some research actually, since I wrote this, some other research is doing at commercial scale now from non-woven. The composite was generated by hand lay, most of these hand lay metrics, and it's done in research labs. Mixing short fibers, whether in labs or high volume production, we have short fibers, and short fibers don't give you really high fiber volume fraction. You require high volume fraction to get high performance. And the research did not take advantage of new technologies such as resin transfer molding under vacuum. We have done in our facility, under my supervision, my leadership, we done composite from cotton, we done 3D woven fabric, and I did presentation in this conference, first Smartx here several years ago. And these are the characteristics of the yarns we used, and these yarns are thick yarns, and virtually it could be from waste. You can take actually roving instead of yarn and make roving, convert roving from waste short fiber. You don't need really long fiber because we need high thickness for the 3D composite to get substantial thickness so we can use it in products. So we used that, and we had a epoxy resin mixed with soy. So it's 100% cotton mixed with 20% soy, and we have 50-50 fiber and resin. So we're talking about 70% green material inside that composite that we done in previous research. And we were able to find composite from cotton is the blue column there. And we will find, you can see that we are very similar in tensile properties to white cedar wood. And we have also better performance than polypropylene plastic. This is pure plastic, what you see on the left. We have 3 woods there, and we have 4 plastic. And plastic are made of cubic chairs with outdoor, indoor furniture from plastic. These exist, and they fail very easily. They crack and fail prematurely because you have plastic and you don't have reinforcement on them. Crack propagation is very easy in plastic. So with this background, we have to cover now the topic of this research, which is truri fiber. Truri fiber grows in the Amazon area and some other area in Brazil, and they are grown naturally, cheap. And the locals there are really still live very simple life. They use the truri fiber, and the truri fiber grows in sack. The sack you see on there, do I have this sack here? Sack closed, and the sack protects fruit of the tree. And the local take the sacks, collect them as you see here on the right, collect these and take them and use them for applications such as roofs, and they do some handbags, very simple products. So our objective is to develop 3D composite. We need to add value to these fibers and measure these properties and find application for these properties based on performance. And most of all, we need to look at improvement of people's life. People's life in this area is almost primitive. They are living in very small villages, and while they are happy with their life, they looking for increased income. So what we did here, very simple. We converted everything green. We followed green processes. The first step to get the fibers, we soak the fibers in water for about during daytime, and then take a brush, take every one of them and brush out to remove the lignin and dust and other material. And then we dry them in room temperature, so we don't use any energy. And then we take them, trim them, and you see what you have on the right. And I have sample here in my bag to show you. This is natural non-woven fabric. They have a mesh there, looks like a mesh of fibers, naturally non-woven. Our resin system is not green. That's the only thing that is not green. We have a contract with Ashland, and Ashland is developing 50-50 soy-based and epoxy-based resin that we plan to use. Normally, when you use soy resin or other natural resin, they are really brittle. They are not as good. So we thought at the beginning we need to try something that will make the fiber strong, as the vinyl ester resin that we use in this case. This is the resin system. You have to mix it with initiator and promoter with certain percentage, and then you infuse the system using vacuum assisted resin transfer molding. And this is our experimental design. We have here 3 parameters. The number of layers. We used 2 of these. When we have the sack, we just cut the sack, and then you will have 2 pieces from the sack. Then we can pile them up for 2 layers, 4 layers, 6 layers, 8 layers, and then we can orient them. 0 degree is the orientation of the sack. 90 degree is perpendicular to that, and then we can take some of these and make them 45 degrees plus and minus. And then we can stretch them. 0 stretch as produced, as collected from the tree. That is a 0 stretch. Then if you take this fiber, we discover that if you take it and pull it, when you pull it, it stays there. So we pulled it 100%, and the fiber orientation was mostly in this direction. Now it became about 45 degrees when you pull it 100% orientation, stretch. These are the 12 samples we have done. If you look at the matrix that we have before, the total number of samples we've done is 12, where you have the first 4 from 2 to 8 layers, we kept them 0, 90, and we kept the stretch 0 as produced. And then we took 4 and 8 at 0, and we changed the orientation to 45 and plus and minus. This is 45 plus 45 and 40. And we determined the fiber orientation system using image analysis, where you have in this direction the sack cross direction, and this is sack direction, which is a 0 direction we consider. The top one here, the fiber structure you see there, one is unstretched and one is stretched 100%. This is a magnified picture. You can see that we created some void. So the fiber volume fraction is expected to be lower at the bottom one than the top one. You get this fiber this way. This is the way we prepare the composite. We stack the preforms, the fibers, and then we do vacuum bagging, and then we do resin treatment and the curing. and then we get the final composite, which looks like wood. You look at it, it has the grain of wood. Very nice look, natural look. We did nothing to it. And it also has glossy surface because of the resin give you that glossy look. So it's really nice piece finished, and I have some small piece with me if you are interested to look at. Fiber orientation distribution function was determined every 15 degrees as we do normally for determining fiber orientation. And then you have here the sac as produced, and we're taking the 0 degree, the direction of the sac, and you can see the fibers concentrated in the 0 direction and 180 direction, which is again same 0. Okay. And then if you take the 090, you will see that we have more fiber start developing in at the 90 degree. So we have most of the fiber now at 90 degree and 0 degree. And then when you do the 45, adding to this 45, minus and plus, you get some randomization. So you have fibers almost everywhere, this way. So that's the purpose of having the fiber orientation, and some people did work with jewelry fiber and with composite, but this is new here. We added this stretch, and we were able to get the orientation the way you see it here. We're supposed to get many products. This is new, and like I said in the title, this is a progress report. The work is still going on. We finished the impact properties, and I got these 2 days ago, and I was up until 2 a.m. today to get the results done and show to you. So we done the impact, and the impact we have this in under my, I oversee a lab, composite lab at North Carolina State University College of Textiles. This is a $1 million lab, got all the equipment needed from manufacturing to testing and evaluation. These are the results of the impact. We took the energy, absolute energy, and then we have the weight, preform weight, we have composite weight and resin weight, and then we determine the thickness, but 2, and then the fiber volume fraction was calculated. So you can see that the top group has more fiber volume fraction, V sub F, and the bottom group has lower fiber volume fraction, as we expected. I thought of taking also the energy as normalized by the fiber weight, which is a preform weight. You can see that in the column 1, 2, 3, fourth column from the left, and the 5th column from the left is normalized by the composite weight. We're trying here to establish relationship between parameters, physical parameters, and performance, so you can design for design products and target products. From the data you saw in the tables, we have here the energy, absolute energy, and here's the number of layers for 2 sets of stretch, 0 and 100%, and the orientation for all this here 4 cases is 0, 90. And you can see here as the number of layers going up, you get more energy to break the sample. And you can see here the 100% seems to be because fiber volume fraction is lower, so you get a lower energy, absolute energy, right? Looking at the results and normalized because of that reason, the case is reversed when you look at the number of layer versus the energy normalized by the preform aerial weight, aerial density. This is a weight per centimeter square. So you can see here the fiber were more effective when you normalize by the fiber weight. If you normalize by the composite weight, same thing. So once you know your weight, you can know the performance. This is good established relationship, ready to be used by engineers to engineer products for certain applications. This is the orientation. We are looking at the orientation 090, and we added the 45 minus and plus. And you can see that when you have the orientation random, somehow the fibers resist better the energy. They impact the energy and give you more energy. One case is obvious and the other case looks like equal. We need to remember here everything is done manually, stretch is done manually, so we have some experimental error that we need to consider here. But if you look at the normalized energy by reform weight, you can see that we have the random orientation produce better resistance to energy, better performance. Okay. This is a composite normalized by composite weight. We have same trend. We have better performance for random orientation. Okay, what's the next step? We would like to conduct here impact failure analysis. Why the impact behavior behave the way we saw it in the graphs and table. We're also going to measure other properties. We're targeting what we have so far. We did a batch, that's enough for tensile. We need to do more for other properties if we're going to continue with this research, and we intend to do that. We're also going to conduct tensile failure analysis to see what happened to the layers. Do we have delamination? Do we have fiber pulling out of the structure or fiber breakage? All this need to be looked at. Like I said, I got the results while I'm traveling. I was in Italy before I came here, so I didn't have time to look at the samples while there. We will also conduct comparison between plastic properties as we done in the cotton research several years ago, and we look at the composite from true fibers. Then we will identify end uses based on above findings. Performance application relationship is very important. This here is what we got from sample ID2, which the details you can see. These are the front of the panel after impact, the back of the panel after impact. And if you look at this impact behavior, first thing it tells me we may have some delamination, and this is normal. When you have layers, that's no Z fiber between the layers to stitch them together. So we're planning to do some pinning in the future if time and resources allow. And also we have another sample here. This is 8 layer. It looks very better sample. And you can see here we have clean penetration for the striker. And you still see in the back some fiber. I believe from this picture, I didn't have the sample in hand. I believe from this picture that we have some fiber pulling out of the resin without breaking. I think so. We have some break, but also we have some pull out. We'll look at that closely when we complete that research. These are the potential applications. These panels, small panels, you can put in furniture, indoor and outdoor furniture. Replacement of wood. We are really getting hard on cutting trees worldwide. And if you understand the benefit of trees to human life, you will never cut a tree in your life. Trees are very important to us, human. So we need to have new material to replace wood. Keep the trees producing fruits and producing air, clean air, filter the dust, filter all kind of issues, protect us from wind, shades. All this here, the trees impact the environment positively. More trees, better environment. So we need to have renewable material to replace the wood and keep the trees safe. So this is a replacement for wood. This is a floor covering. We all have to floor covering. We like wood. Many of us like wood. And this is really, you can make these with this size directly. You can make these wood panels and put them in the floor side by side without any trouble. You can make them same size, cut them, and they are ready to make. Resin treatment, dry them, cure them, cut them, put them in the floor, and put other furniture. Construction is potential application for that. Well, what we do, natural fibers are naturally weaker than high performance fiber from synthetic, from petroleum based. However, we know that there are processes, chemical processes that can enhance the fiber strength. For example, I worked many years ago in the 80s, I worked in project stretch mercerizing of cotton. We stretch cotton while we are, after adding caustic soda, and stretch it, and while we are neutralizing it with acetic acid. So we can, and this research proved to us, we can make the cotton 100% stronger, 80% to 100% stronger if you do stretch mercerization at the fiber level. So if you look at what is the most fiber used today in application like boat and houses and many, many things, fiberglass. We have a flax variety that is very close to fiberglass. Trori fiber is cellulosic fiber. Cotton is cellulosic fiber. But we can match some of the high performance fibers if we take care of natural fibers and treat them well. We should be able to get performance that's similar to fiberglass at least. Then we can get rid of fiberglass. While fiberglass is made from silica, sand, which is abundant. Its problem is it is not biodegradable. And this is an issue. Where are you going to put this waste material in the future? Landfill is becoming scarce and very expensive. So we need a biodegradable material that has the strength of fiberglass. If you are able to do that, you can capture a market that billions of dollar market worldwide. And like I said, flax, some variety of flax are close to fiberglass. With some treatment, you can make it to fiberglass. With this, I'm closing my call, and I'll be happy to answer questions if the time allows. Thank you. Looks like I have to take questions later. Sorry, Dr. Saad, I was between your two talks.